of you come back and actually judge those prizes. And so what we decided to do, and this is where the funding goes now, is to have a first prize of £500 and a second prize £250 for the best prize, judged by the alumni who come to meet our fourth years and talk to them about their projects. And then we invite back the prize winner, the person who won the top prize, to come and give us a presentation on his or her fourth year project. I'm absolutely delighted that Anna's been able to come back and give us a presentation on her winning fourth year project. Anna Roomans to give us this presentation.
Hello, good afternoon. So today I will be talking about a topic which a number of you might have listened to on the news recently. It's diagnosing retinal diseases using artificial intelligence. And my work, sorry, I don't know if you can see me, my work last year with my projects had a similar aim, obviously to a much smaller, modest extent, but I hope you will still find interesting, because the overarching aim was to create a tool that used medical imaging to diagnose retinal diseases, as I have said. And the disease I focused on was an inherited retinal disease. It's called Stargardt disease. But the manner in which I did it means that it's replicable to a number of other diseases. So the imaging modality I used is called OCT. This stands for optical coherence tomography, and it is widely used in ophthalmology throughout the UK and a number of other countries. And it works, it is a non-invasive technique first of all, and it works by low coherence interferometry. So actually what we are looking at is a cross-section of the retina, and we are able to visualize this because all of the retinal layers, as you can see, would have like different texture, and that is because the tissues have different optical properties. We are mainly interested in the back of the center of the retina, so that's where we see the foveal dip there, mainly because that's where a lot of the degeneration will initiate. What we are actually looking at is just a 2D scan, but this is just one in a 3D volume, which is made up of these such scans. And so there's a lot of information which the doctors don't necessarily have the time or ability to fully comprehend, and that is why there is a lot of potential to automate such a process, because we as humans aren't really able to comprehend the entirety of the scan, but computers have been designed to deal with such a huge influx of information. So why not use it in this field as well? Because it would allow us, A, to have the possibility of more accurate diagnosis, so we'll have a second opinion to what the doctor's conclusion was, and also to streamline NHS waiting lists, because at the moment so many of these scans are being done, but there's just not the manpower to sort through them and actually get the urgent cases seen before and such. So there's a lot of benefits if we manage to do such a thing. As I mentioned, I worked on Stargardt disease, and as with any problem, you've probably found the most important thing is to actually understand what we are dealing with. So my first step was to sort of determine what aspects or features of the data clinicians looked at in their own diagnosis. So very briefly, the way the degeneration occurs, it is localized. So it starts in the center, in the foveal pit I mentioned before, and sort of spreads out, and the retinal layers collapse on top of each other. So what is relevant to us is sort of extract the layers and be able to perform quantitative analysis on them. But the problem comes because, like most of medical imaging in general, the way in which the images are acquired renders them with like poor contrast and a low signal to noise ratio. So say we wanted to extract these layers, we can't simply use an edge detection algorithm because it will just fail. So we're forced to get quite inventive about how we approach the problem. So as I see it, the crux of the problem is to be able to create a tool where the doctor doesn't need any input, so it to be fully automated and general. So if we look at the images, on the right we'll see a healthy example. we could make assumptions about what the algorithm would find, say 5 layers, these range of intensities. If we now look at the diseased case, given the huge variability that there is patient to patient, we can't make these assumptions. And so we are forced to, again, get more creative about how we do it and not just simply impose, if we find this, then it means this, that sort of way of looking at it. So when I was creating the blueprint of how to approach the problem, I sort of 2 avenues. I could either mimic the steps that were being taken by clinicians now, sort of extract the layers, see what state they were in, where the degeneration was happening, and from there come to a conclusion, or use the more exciting black box approach, where I would simply feed the image into this architecture, and then out comes a class, say, it is healthy, it is unhealthy, it is this level of degeneration. And I think there's obviously merit in implementing both, and that's why I did it. But I wanted to go through the traditional approach first to actually see whether the data had discriminatory ability and just sort of evaluate its capabilities. As I've said, the traditional approach mimics the steps taken by clinicians. So we want to extract these layers and again perform quantitative analysis. And the aim was sort of to produce a colour map such as this, so that it would be very visual to the clinician where the degeneration was and also how extensive it was as a way to grade where the patient stood on the scale. And so to do this, I wanted to create a model that was localized in terms of where I was looking at the scan, and again, very general and fully automated. So the first step is not very interesting, it's just simply getting the data as clean. That's quite obvious why we want to do that. And then we are going to fit a model. Again, I'll recap, we want a fully automated tool. And so my decision to fit a model was that I could incorporate current medical knowledge. Why throw that away when it's very, very useful, but without making these assumptions. So the first thing was to find the foveal depression, which where it starts. It's logical for the machine to know where this is, and then bound the region of interest of the data we're looking for. I don't know if you can appreciate it, but the blue region isn't actually a full region, it's a number of different columns. And this was done in an effort to incorporate how we know the disease progresses, as in it's relevant for us to know where in the scan we are in relation to where the degeneration starts, so we can again assess how extensive this is. Coming back to the point of traditional methods not working on this low quality, like poor quality data, in order to find the edges, what I did was I classified pixel by pixel using a very simple support vector machine, whether they belong to a boundary or not. And this comes out. And it is obvious that it does find the layers, but without a global view, which I haven't given it because I haven't given it any prior knowledge. It has no idea what it's looking at. And because I wanted to avoid it, this method just wasn't valid. And so I simply used it to, again, create this model from which I then went. And I was racking my brain thinking, how is the machine going to know what it's looking at if I haven't told it? How can I create a general tool that's fully automated? Like, doctor doesn't need to input anything. And as again, you've probably found, is usually the simplest solution when it turns out being the best. So if you think of a retinal layer in an eye, it makes sense that it's continuous, right? One part of the layer is not going to be here and the other one there. So what if I could model the layer as having a sort of homogeneous colour and saying that all pixels were adjacent? What if I modelled it as a superpixel? So each layer per column was a superpixel, and that's what I did. So I basically readapted the algorithm, which has been used as called simple linear iterative clustering, but that's not important. It's used mainly in computer vision, and applied it to this problem column by column. And then, as you can see, there's a few errors that was simply refined using a graph search. And the great thing about modeling a layer as a superpixel is that it is able to take degeneration in stride. It is not, this algorithm is not forced to find a specific number of superpixels or layers. So it is very easily adaptable. In one case it can see 5, in the next be like, actually there's just 1 in this location, and it just takes it in stride. And the other great thing is that it naturally encodes information about the layer, because if we know how many pixels are in this layer or superpixel, and we know where all the pixels are, then we have a lot of information about the state, the size, the shape, everything. So now that we have this information that we've been looking for, we just need to be able to classify it. So again, I won't go into detail, but for those of you who are interested, I just used principal component analysis. So basically condensing this multi-dimensional data into just 3 dimensions. Obviously here all physiological relevance is sort of gone, because you're just transforming it into the most statistically significant directions. And as you can see, the 2 classes are quite distinctly separated. Well, each point represents one of the columns I was talking about. So then they can sort of vote which side of the line they fall on. And I simply trained a decision, like a classifier between both of them as a support vector machine as well. And so new data would come in, and depending what side of this classification boundary they fell, I was able to say, okay, they were healthy or they were unhealthy. And similarly, once I knew which ones were unhealthy, I could repeat a similar process, and depending on what cluster they fell into, I could create a color grading, such as that below. And luckily, this was actually really, it produced really good results with over 99% accuracy on test data. And as is to be expected, the more images we use for training, the better the accuracy and the better the robustness, which is shown by how the green lines are getting smaller and smaller. And I think the most interesting thing about this isn't that the results were good, but more that it was done in a way which was clinically relevant, because as we know, in most medical applications, trust is a very important thing. And so by mimicking what clinicians do, we're able to support their own decision making. They don't necessarily need to just trust what I say. They can look at how for example, the layers were segmented and see if they agreed with this. So I think this is the most important conclusion to get out of this. And once I knew the data had the ability to do this, I was like, why not see how deep learning performs with this sort of data? So instead of me being like, okay, these layers are the important features, etc., etc., it would just learn which features to find interesting, and well as at the same time as learning the classifier. So the problem with this application, and basically every medical application, is there's just not enough images in comparison with the natural images available for other networks, for example, for natural image recognition. This is to do with the fact, especially for the rarity of this disease, there's just not enough patients to scan. And secondly, it's a small miracle to get clinicians to take the time to painstakingly annotate all these images. So I was very happy to have 752 scans. And also I think it makes it more interesting how you approach the problem, because you can't just feed it by brute force more and more images in the hope that these will happen. So I approach the problem in 2 ways. Firstly, I reduce the number of parameters that need to be learned. So the actual network is not important, but the idea was getting knowledge used to solve one problem and using it in another. So the first part of the network I used from a network that had already been trained on natural images, and I left it the same in the hope that it would extract features such as edges, which were general to any problem, and then simply trained the last bit of the network to be more problem specific. And this classified the entire image into healthy, severely diseased, and mildly diseased. So just 3 classes for the entire image. And my second approach was, why not, on the other hand, just use a very simple network, very basic, one which was created just to identify numbers, handwritten digits. And instead of feeding it the entire image, essentially do the same as I'd done for the traditional approach, so break it up into localized parts and feed the individual ones, which effectively multiplied by 60 the size of the data set. So that's what I did. I fed each one individually, and again this allowed me to create a color map, because each individual column was graded, and then so it would come out here and then like that. And again, it produced quite good results. The transfer learning was almost 100% accuracy, and the rest was around 90% accuracy. Obviously, I would say, because we really don't know what's happening in these modules, a lot more work would be needed to be done. But I think actually the most interesting thing in this application is to see what the machine finds interesting, what the machine finds relevant. Because at the moment, clinicians look at certain parameters, but I think it's an interesting exercise to see what the machine think is optimal to discriminate between these two classes of healthy and unhealthy. And talking to clinicians, they actually find this, one of the most exciting applications. So far, I hope I've convinced you that there's definitely potential to implement this into the clinical workflow, and that there's value in doing it in a way which is relevant to the people who are going to use it at the end of the day, which are the clinicians, and that trust is very important. So actually, a lot of dialogue should be had with them in order to see what they want as a tool and what they need. And there is so much more work that could be done, mainly finding the thing I see as potentially the most relevant and interesting is actually, okay, so if you think a doctor doesn't just look at one scan, a doctor will talk to the patient, will see its history, will see its family history. There's just a lot of variables that that we take into account. And at this point, the machine is just looking at one scan and potentially not even sometimes a full 3D volume. So I think a lot of work could be done to sort of create a more global tool. Just finishing, on a personal level, I think I've learned a lot, and I'm quite excited to continue down this sort of line. And I hope future fourth years will also find something they really like. And please, if you have any questions, either ask now or at the end.